We're going to look at silicon neurons today, and yeah, go through some examples of neuron circuits. And just yesterday morning or yesterday afternoon, we got the new class chip to work also with these circuits. So you'll be able to do labs and measure from the things we will see. But before going into circuits, I would like to just give a brief overview of what neurons are, and so that we know then what we can want to model. And in terms of complexity, real neurons are actually among the most complicated cells that we have in our body. Unlike all other cells, the neurons, they have very specific morphology. They have very strange shapes, unlike, I don't know, blood cells that are all spherical and identical. And it's a classical example of a system in which the structure determines the functionality. So the shape of the neuron and the shape of the architecture, the structure of the architecture determines the functionality. And in our case, we're interested in computation. So in terms of complexity, real neurons, of course, are the most complex things, the things we want to simulate or emulate. But if you try to reduce the amount of complexity and still be close to biology, in order both to understand biology, but they maybe obtain some of the computational advantages of real neurons, the next step is to do conductance-based models, and we will see those. And then if you want to reduce further the complexity of a single neuron, you can go to integrate and fire models. These are models of neurons that integrate their inputs and then produce an action potential, which is considered an all or none event, like a digital pulse. Now, why would someone want to reduce the complexity of a neuron if you want to, stay close to biology? Well, the thing is, there are limited resources, and complexity requires a lot of CPU in case of software, or a lot of area and memory in case of hardware. So if you have limited resources and you want to create a large network and you want to put many neurons, it's just not feasible to put circuits that model in great detail all the single proteic channels of a single neuron. Even though you have real time with silicon, it's just going to take too much area. And there's many other problems. For example, how do you connect neurons together? In our brain, we have, the nervous system uses all 3 dimensions, but on silicon, essentially, we have 2.5 dimensions. We have basically the active area, which is on a 2D plane, and then we have some metal layers that allow us to connect things nearby. But the brain, as you know, has foldings, and it actually uses 3D in an optimal way to determine or create the structure that determines the optimal computation. And so our technology is still not advanced to the point that we could actually reproduce real brains. And if we use silicon, we are stuck with this 2D.5, or basically 2D technology. And even if we use conductance-based models, you'll see it actually requires quite a large amount of area, and there is complexity in the circuit design in addition to the complexity in the computation, and other disadvantages that we will see. If we reduce the model to a simpler one, like an integrate and fire one, we can get away with a small number of transistors, maybe 6, 12, not more than 30. And then put many of them, we can put billions of transistors on chips, so we can put many millions of neurons on chip. And of course, if we reduce the complexity even more, and what we say is, it doesn't matter if the neuron integrates and spikes. What really we want to look at is the average activity of a neuron over time, which is the rate, the firing rate. And if we look at that, we can simplify even more. And you can go to the extreme where you say, I just think of the firing rate as something that changes smoothly in a way that saturates. So it's like a sigmoidal unit. And you already know that we can implement sigmoidal units using the transconductance amplifier, so just 5 transistors. Or if you want to simplify even more, you could say, I'm going to use a linear threshold unit. So I remember we talked about ReLUs last time. Linear threshold units are essentially model neurons that take the input and then produce an output that is linearly proportional to the input if the total sum of the input is positive or above some threshold, and otherwise it's zero. So it's still a complex device because it has a nonlinearity, this max between a threshold and the output. But it's very simple, and you could even do it with a simple current mirror. So if you want to do linear threshold units using analog circuits, all you need is a single or maybe 2 transistors to do the neuron functionality. So that's basically, we will actually see all of these examples. These ones, the sigmoid and the linear thresholds, we've already seen. As I said, you can do them either with a current mirror or with a transconductance amplifier. So we'll focus more on the integrated fire and the conductance-based neurons, and see the analogies, the advantages of one versus the other. But before we go there, I just want to give another quick introduction and summary of real neurons, what real neurons are and why they're such beautiful cells and so powerful in terms of computation. And if you look at what exists in nature, you'll see, as I told you, they have all sorts of different shapes, and the morphology of the neuron determines the functionality. These are different types of neurons that are found in different parts of the actually different animal systems and different parts of the brain of the various animals. So this is an example of an inhibitory cell in the cortex. This is an example of a pyramidal cell in the cortex. You'll notice that all the cells have a cell body. That would be the soma. Then they have an arborization nearby around their cell body, or close to the cell body, and that's the dendritic tree, which has input synapses. So this is how the neuron receives all the input signals. The fan-in, if you're thinking about logic gates in digital circuits, usually logic gates have a fan-in of 2, 4, maybe 8, 16. Here, the fan-in goes from 1,000 to 10,000. So it's really, really different from Boolean logic or just logical operations. And you can see there are some examples of cells that have very complex dendritic arborizations, and on each of these fine lines, there could be tens of synapses. So that's the input, and some cells have dendritic trees that are clustered like a daisy in different areas. Like here, you could see there are 2 arborizations that are sort of complementary. Some have uniform spherical-like dendritic arborization. Some have, and these are the ones that we have in our cortex, in our visual cortex, local dendritic trees. So the cell body is here at the center, and then they have proximal synapses on these local dendritic trees, and then they have distal synapses on dendritic arborizations that are far away from the cell body. And this is an example where you can see that the cell is actually collecting signals from 2 different areas. One area could be like the bottom up. In case of in the visual cortex, for example, this area could be receiving signals from the retina, from your sensors. And this area could be receiving top-down signals from higher areas where you could have, for example, a prediction of what you expect to see if you're doing predictive coding. Or the prediction of the pattern that you're expecting to receive. And then you can imagine that these will sum up or in different nonlinear ways, and then they will make the neuron fire or not fire if what you sense from your sensors matches or does not match what you expect to see, and so on. As I said, there's many examples of different cells. These are cells in the cerebellum. This is an example of a cell that is just collecting parallel fibers that just go across and connect to all these dendrites. There's millions and millions of these axons of of other neurons that go and touch. So the axon is actually the part of the neuron that goes out of the cell body and projects the output signal. They're not shown here. So here we only see the dendrites. The axon is typically a very thick and long, not typically, it can be very thick, but it's typically very long process that comes out of the cell body and goes out. In this case, it would just go off the paper. It was really off scale. It would just go into the next room even and connect to other neurons. So input is received on dendrites and output is sent to the axon. And then from the axon, it's propagated down to the destination. And the axon also is not just a single output. It's not a fan out of one. The fan out, of course, has to be sort of self-consistent. So it can fan out to hundreds or thousands of neurons. And then if you have tens of these connecting to a single neuron, you have tens of thousands of inputs. So the axon typically is a long wire, and then it has arborizations also. It basically, the axon splits up into different sub-processes that branch out. And then you can imagine that a neuron connects to neurons nearby, then maybe it skips some neurons, and then it connects to neurons far away, and then maybe to the neurons on the left or on the right, or because it's 3D, it could be north, south, east, west, up, down, all possible. And they're typically, it's again not homogeneous, it's with clusters which determine the functionality. For example, in the visual system, if you have all neurons aligned vertical axis that receive inputs from the thalamus, which receives inputs from the retina, then that particular neuron that has the dendrites aligned along the vertical axis would be sensitive to vertical bars. So if you're moving vertical bars across, that one neuron will fire when the vertical bar crosses its receptive field. Similarly, you could have neurons that are receiving inputs from horizontally aligned cells, and you would have neurons that are tuned to horizontal bars. And you can imagine you can combine, you can increase in the hierarchy and have more complex patterns where you have T-junctions, crosses, all the way to recognizing faces, combinations of circles with vertical bars and horizontal bars that somehow produce an output if the combination of all those patterns is consistent with the geometry, which would then be, for example, a face recognition cell. So that's what I mean by the structure determining the functionality. The way these neurons are connected and the way these axons and dendrites are arranged really determines what they do. And typically in biology, there's always these topographic maps from the retina to the cortex, but you can imagine also in the auditory system, you have space, frequency, time represented as a 2D map. And then you could have a tonotopic map where the position in the map determines the frequency, and then the time at which it arrives also determines the type of pattern that you're trying to classify. So neurons are quite complex. And as I said, it's very difficult to simulate on computers or even, pencil and paper with equations, these complexities. And you can start to simplify them if you really want to try to understand, how can we use neural networks to do computation. And one of the most successful ways of understanding how neurons work was the work of Hodgkin and Huxley, who really were among the first to say that there was an equivalent circuit in terms of electronic components that could approximate the electrical properties of real cells. So real cells produce action potentials through electrical, ionic currents. And so you can really model them with electric components. And here we have an example of a low-pass filter, so an RC circuit, where you have, in neuroscience, typically you don't talk about resistances, you talk about conductances, but it's equivalent, as you know. And so here you have a leak conductance, which is just a constant resistor, and a membrane capacitance. So the bilipid layer of neurons of every cell is a perfect insulator, and it separates what's inside the cell from what's outside the cell. And it can be simulated or emulated directly as a capacitance. It's a really faithful model of the function of the bilipid layer of a cell, of a neuron in this case. The leak conductance models the population of ionic channels that allow ions to flow through these channels to go from inside the cell to outside the cell. And as soon as you change concentration of ions from inside to outside, you have flow of ions which are charged, so you have a flow of current. So this is actually a perfect, a one-to-one approximation or emulation of what's happening in real neurons. In real neurons, you have ions that have their mobility. In electronics, we have electrons. But except for this difference in the mobility, the physics are exactly the same. So if you change the concentration of electrons from inside to outside, you change the flow, and then you can measure that with the resistance. And this is exactly what's happening in real cells. And if you measure data from real cells and you measure data from NRC circuit, you can map one-to-one. You can just fit perfectly well. Then you'll see there's these other conductances that are shown here in this drawing. These represent, in this particular case, sodium and potassium. And these are voltage-dependent conductances, meaning that the value of the resistance changes with the voltage. And in real cells, in neurons. And in neurons, if you actually change the membrane potential, you open up or you close more or less ionic channels. And this is actually a positive feedback effect. If we increase the membrane potential, we open up more channels, which allow more current to flow, which charges up the capacitor, which increases the membrane potential even more, which opens up even more. So you can imagine it's an avalanche effect. And as soon as this positive feedback loop kicks in, it only kicks in if you go above a certain threshold, then you have this abrupt avalanche effect, as I said, and the membrane potential just goes up. So here you see it. As soon as you go above a certain threshold, you start to open these channels. They allow more current to flow, which opens them up even more, even more, even more. And this avalanche effect is actually gives rise to an exponential behavior with a positive exponent. Of course, if you don't go across this threshold, if you just stay low, you only activate the leak, the passive part of this circuit, which is just our RC filter. So you have just an RC increase. That would be 1 minus e to the minus t over tau. And then if you stop injecting current, you just decrease with e to the minus t over tau. It's a pure linear filter. But if you activate these channels and you go above the threshold, you turn on this positive feedback, which is just this goes bang to the max. Of course, this is a physical system. You cannot go to infinity. It has finite resources. So whenever you hit the limit, in our case, in circuits, hit the power supply limit, you stop. In biology, there is actually sodium activation channels, which are the ones that are responsible for positive feedback, but also sodium inactivation channels that actually stop this positive feedback loop. As soon as you reach some threshold, there is an active mechanism that stops this avalanche effect. So you go up really quickly, you spike, you do bang, and then you stop. At that point, when the membrane potential is way up and after some time, the negative feedback effect kicks in. So there are potassium channels that start to open up. They're much slower than the sodium channels. So first you have this positive feedback effect. You have enough time to just go up. And then slowly these start to open. And when they do open, they have the opposite effect. And they discharge the membrane capacitance. And they bring the membrane potential back down. And in fact, because these are slower than the sodium potassium, when you go below the threshold, these close. There is no more current going in. You're only discharging. And because these are slow, you keep on discharging for even longer. And that's why you go even below the resting potential. So if you start from some resting potential, whenever you go up, you spike. Then when you turn on the potassium, you discharge. But then you keep on discharging even below the resting potential. And then at some point, these will also start to switch off. And then you have your passive leak, which is again an exponential part here, and you go back to your resting potential. So this is basically intuitive explanation of how action potentials are generated in cells. that have these active channels that start to open and close depending on the potential, on the capacitance, on the membrane potential. This is actually what Hodgkin and Huxley found when they were measuring squid axons, and they derived the equations that describe these positive and negative feedback loops. And that's how they got, this was in the 50s, late 50s, and they got the Nobel Prize for really discovering this, because they can really, again, fit one-to-one the real action potentials with these equations. And this was the 50s. You have to imagine there was no MATLAB, no calculators, solid state calculators. They were actually doing all the number crunching by hand and solving all these differential equations by hand. There are some very nice articles that explain the history of how Hodgkin and Huxley actually managed to find out how to model action potential generation mechanisms just by looking at the data from biology. And in fact, a nice anecdote says that because they had to go to war, they were studying these in the early 50s or maybe even the 40s. Then they had to go to war. They had to interrupt the research to actually go and serve in the military. And then several years after, I don't remember if it was 4 or 5, they went back to their research. And because they were academics and in the military, they needed people that would learn about control theory and mathematics. They started studying those things. And then when they went back to biology, they managed to take advantage of all of the know-how they got from studying control theory to solve ballistic differential equations for understanding how action potentials work, and then went to the Nobel. So it's a nice example of how math and control theory and engineering influenced neuroscience and then led to the Nobel Prize. So we will see actually circuits that can implement these positive feedbacks with transistors, not just voltage control resistive elements. This is, again, a very simplified explanation of how real neurons work. And depending on the parameters, the properties, how fast these channels are, how quickly they open, how long they last, what are the dynamics, you can get different shapes of action potentials. So here there's examples of how exactly the sodium and the potassium channels open whenever you depolarize the membrane potential by injecting constant current. So if you have a step, this just goes up, it will then turn on the channels. And I told you sodium is faster, sodium turns on fast, so there is enough time for the current to go into the capacitor. The membrane potential goes up, it spikes, and then after some time, potassium turns on, it's slower, and sodium switches off because of the sodium inactivation channels. So in this period of time, you discharge the membrane capacitance, and then you keep on discharging it even after you finish the whole action potential generation mechanism, and then you go back to the resting state and you can do it again. So this is exactly what's happening in biology. This is, as I said, is the simplified explanation. And as I told you, depending on which animal you look at, which part of the brain you look at, these sodium and potassium channels have different dynamics and will lead to different shapes of the action potential. I should say that there's many more channels in a neuron, not just sodium and potassium. There's chloride and other proteins that are involved. These are the main ones. Another channel that is important is the calcium, and we will see also examples of how modeling calcium channels with electronics can lead to interesting neural, or can explain interesting neural properties. And this is an example of different action potential shapes. So all neurons of every animal species, from insects to humans, they have this property of generating action potentials. As I said, depending on the speed of the channels and other parameters, they can have different shapes, but everyone has this feature that you integrate, you reach a threshold, you spike, and you reset. So this is common to all animal species. And even though the shape might be different from different parts of the brain or different animals, the overall principle of integrating, spiking, and resetting is present. And that's why it's possible to simplify the computational aspect of neural communication and neural computation to integrate and fire as well. So some mathematicians and some neuroscientists claim or believe or are considering the fact that the shape of the action potential has an important computational role, but most computational neuroscientists and now AI and computer scientists are assuming and hoping that just by simplifying the function of a neuron to integrate and fire, it's possible still to reproduce many of interesting computational properties of real animals. So it's still not clear whether the specific shape of the action potential is really important for computation or not. But you should be aware that the shape can change depending on the number of channels that you simulate, their dynamics, and their properties. So again, if you have any questions at any time, either just talk, interrupt me, or if you write in the chat, I still see it here. I still can reply. Okay, so for what concerns computation, the fact, of course, every animal has cells that fire, but what is also common to all these animals is that whenever you have these neurons that produce action potentials, what happens is that the larger the input current that is being injected or that these neurons receive, the faster they will fire. So the higher the firing rate. So if you just stimulate these neurons at some current, you will get some output firing rate. And if you increase the current, you increase the output firing rate. Actually, there is a very nice linear range where if you double the current, you double the rate. So these neurons, for some part of their activation function, behave as a linear current to frequency converter. Sorry, I pressed. The other features of spikes that you should that we should remember for when we look at the circuits is the fact that they have a refractory period, meaning that just after they fire, because of the sodium activation channels being still open, no matter how much current you push in, it will not fire. So there is a period after which the neuron is just silent, and it will take some time for the neuron to recover before you can actually get it to fire again. And this period in which the neuron is just silent, no matter what you do, is called the refractory period. And then another feature is the fact that it's a physical system. You don't have delta Diracs in nature. So these spikes that even though they're very, very fast because of this positive feedback avalanche process, they do have a finite pulse width. And this also then, in terms of mathematical modeling and circuit, has an effect that we will see. The effect of the refractory period is easy to see right away. If you keep on increasing the current, you will keep on increasing the firing rate, which shortens the distance between spikes. But at some point, you cannot go shorter than the refractory period. So if you see it as a curve where you have the spike frequency on one axis and the input current on the other, as I told you, there's a linear part where if you double the input, you double the output. But depending on where you put the refractory period, the firing rate at some point will saturate. You cannot just go faster than what is limited by 1 over the refractory period. And so this, if everything, again, is a physical system, it's smooth. So this smooth saturation effect is like a sigmoid, is an S-shaped. So you can model this with a sigmoid. And if you're interested in very, very simple models of neurons, of activation functions of neurons, using a sigmoid is a very effective way of doing it. And in fact, the early neural networks in the 80s and 90s were using sigmoids all the time. All of the neural networks, if you look at the literature, was using sigmoids. Of course, computers were slow. It was very difficult to either solve complicated differential equations with sodium and activation channels and dynamics. It was even difficult to simulate spiking neural networks. And so most of the neural networks that were being simulated on computers were using sigmoidal activation functions. To carry on with this history part, then there was the winter of neural networks. There was not much neural network development in the 90s and early 2000s, but with the advent of GPUs, large data sets from Google and others, and more computer power, neural networks became popular again. And at that point, people started to increase the scale of the networks. So even though computers were more powerful by using neural networks with thousands of neurons or millions of neurons or billions of neurons, like in GPT-3, even doing sigmoids became too CPU intensive. And so the most recent neural networks now are using ReLUs. They just use half-wave rectification, where you just have a linear rectified unit. And they don't simulate this exponential curve here, which requires, CPUs. So the most recent neural networks use ReLUs, even though in the 80s they were using sigmoids. Okay, so now we're going to look, if there are no questions up to now, sorry, let me close the door. If there are no questions up to now, we can, on the sort of the history and the biology and the math, we can move on to circuits and go to look at hardware implementations of silicon neurons. So hardware implementations of spiking neurons are actually relatively recent, even though the first artificial neuron, in terms of conceptualizing it, was done in the early 40s by McCulloch and Pitts. Hardware implementations of the McCulloch and Pitts neuron not spiking date almost back to the same period, so they're very, very old. Spiking neurons, on the other hand, are more recent, even though they're still in our terms very, very old, and they go back to the late 80s, early 90s. One of the first, if not the first person to propose an implementation using CMOS of a spiking neuron was Carver Mead and the group of Carver Mead at Caltech as I said, in the late 80s. And the circuit that they proposed is called the axon hillock circuit. So the axon hillock is that part of the neuron that's just at the border of the soma and at the beginning of the axon. And that's the place where this action potential generation mechanism is situated, it takes place. So they called it the axon hillock circuit. We will see it, it's relatively simple. And it was proposed by Carver and his students in the late 80s. This was the simplified integrated fire version. The first student of Carver Mead was Misha Mahol. Misha Mahol was a biologist, and she was interested in replicating more detailed properties of action potential generation mechanisms and dynamics. And at Caltech, she was, as I said, she was a student of Carver, and while Carver and other students were looking at the simple integrated fire version, axon hillock, she was working together with Rodney Douglas, who was the founder of the Institute of Neuroinformatics. At the time, he was associated with Caltech, and he was a professor at Oxford, and he was he's a medical doctor by training. Misha is a biologist by training, so they were really into the detailed neurobiology of how neurons work. But of course, being at Caltech and working with Carver, Misha was also interested in building circuits that would simulate those. And Rodney as well was very intrigued by the fact that you could use the physics of silicon to reproduce the physics of real cells. And together they designed and proposed the first biologically plausible silicon neuron. And it was, we will see it in the next slide, it was such a nice circuit, and it was replicating the physics of real neurons so well that it even got the cover of Nature. This was 1991, so it was still many, many years ago, but it's still one of the most faithful models of circuits, electronic circuits, that reproduces the physics of real neurons. At that time, it was actually, everyone was very enthusiastic. First of all, in neuroscience, everyone thought that the star of the show, the main building block for doing computation in the brain, was the neuron. And by building silicon neurons that were so close to real neurons, everyone thought, okay, it's just a matter of months or maybe just a few years, and we can build artificial brains in silicon. Of course, neuroscience realized that it's not the neurons, it's the synapses that are responsible for all the computational complexities. I mean, it's both neurons and synapses, but synapses play an important role. It's not only neurons. And then also in electronics, we realized that building neurons alone is not enough. You need to actually connect them together in the right way and have extra features, nonlinearities, and properties to really do the computation. So even though everybody was very optimistic in the 90s, sort of reality brought us back down and made us realize that in order to really build complex brains, even of a bee, there's still a long way to go. It's not something we can think of doing in the next couple of years. And this is true even today, even though we have much more advanced technologies, much more understanding in neuroscience, there is still a long way to go to understand how to really build a complicated structure, like, for example, the cortical column that is just one building block in the cortex, in the neocortex of our brain. Again, sorry if I keep on doing these historical digressions, but let's look at the actual circuit. So this is the conductance-based silicon neuron that Misha and Rodney proposed. It's relatively easy to go through, so I want to go through this with you. I think we have enough time. So there are these different building blocks, the passive leak, the sodium current, and the potassium current. So the passive leak is just a follower integrator. So you should know exactly, very easily, how it works. The follower integrator, if you remember, it's an approximation of an RC circuit, which, again, if you remember the simplified electrical explanation of how an action potential is generated, is really the passive part. It's really the easy part. So what we do is we inject constant current into this node, which is the membrane capacitance node. In fact, it's connected to the membrane capacitance. If we inject constant current, this capacitor will charge up. And then if this follower integrator is working as, in subthreshold, it will actually approximate first order differential equations. So this is just going to charge up Vmem exponentially like an RC circuit. If we don't increase Vmem too much and we stop injecting current, then Vmem will start to decrease exponentially as well. So this is just a passive RC circuit where we have, again, the rising part, which is 1 minus e to the minus t over tau, and the decaying part when we stop injecting current, which is e to the minus t over tau. Now let's look at the sodium block here. So as we inject current, Vmem increases. This is another follower integrator. So we are basically copying Vmem from the input to the output with some delay. It's a low-pass version of the input. So the follower integrator, in this case, the main role of this follower integrator is to act as a delay element. So on this node here, at the output of this follower integrator, we have the delayed version of Vmem. And then we compare that to a threshold voltage. So this is acting as a voltage mode op-amp comparator. So if the membrane potential is below the threshold, the output is high. If the membrane potential is above the threshold, the output is low. So if the membrane potential is below the threshold, the output is high. That means that the gate of this PFET is VDD. So this is switched off. All of this block is switched off. So when we are at resting, assuming the resting potential is below the threshold, when we are at the resting potential, which is this E leak, this part here is switched off. And this is the same. The direct version is also switched off. When we increase membrane potential, then we have to check what's happening here. And we are comparing the direct version of Vmem and the delayed version of Vmem. So when we reach V threshold and go above V threshold, the first op-amp to turn on is this one. The output will go from VDD to 0. So we turn on this PFET and we put 0 here, but this PFET is switched off because this is still, the delayed version has not reached that level yet. So we only have INA on being synced by the op-amp because Vmem is higher than V threshold. So this IA NA on is being copied back into the input, which then increases Vmem even more, which then makes INA on increase even more, which copies even more current on. So this is this positive feedback effect that I mentioned. You have to realize this is an analog circuit. So as Vmem starts to reach V threshold, INA starts to turn on very weakly. Then as Vmem starts to go slightly above V threshold, we're in the linear region of the op-amp. INA on starts to increase even more, which pushes even more current into Vmem, which increases Vmem even more, and so on. So this is the positive feedback. And that's when we go from rising exponentially to rising with a pure exponent, with a positive exponent. So it starts to go bang towards VDD. After some time, though, after a delayed version of Vmem, after some time, when the delayed version of Vmem crosses V threshold, we turn on INA off, which copies this current here. And now the current that is being synced by the first op-amp, INA on, does not come from the outer current mirror, but comes from the inner current mirror. So we can basically supply all the current from this here. So essentially, we don't need to push current into the memory capacitance anymore. We stop pushing. So Vmem went up. It almost reached VDD. Depending on how fast we can stop pushing. And then it basically stays up for as long as we stop pushing. Then now we can look at the potassium. So again, there's a follower integrator here. So Vmem is delayed. This, to be able to simulate biology, this follower integrator should be slower than this follower integrator. So the potassium channels are slower than the sodium ones. But after some time, so we are assuming that after it spiked and it went up and it stopped pushing, the delayed version of Vmem also crosses V threshold here for this one, for this op-amp. And this op-amp is turning on a PFET and then an NFET. So we flip the current twice. So now we sink current, we don't source current, and we discharge the membrane capacitance through this IK loop. And that's basically the same as the potassium channels in real neurons and in this simplified RC circuit I showed you. And so then we start to discharge Vmem, and then at some point Vmem will go below V threshold. It stops, it switches this off. At some point, the delayed version of Vmem goes below V threshold, it switches this off. And this lower delayed version of Vmem goes below this threshold and it switches this off. And so then we go back to this passive case where Vmem is being pushed passively with an RC behavior to E-leak. Yes, sorry, now I can see the questions. It seems that the part of the refractory period is determined by the sodium channel, not only the potassium. So the refractory period, well, because the sodium channel switches off quickly, the only part that keeps discharging Vmem towards a negative, so some voltage which is below I leak, is the potassium channel. So only the potassium circuit is responsible for keeping the capacitor discharged. So the refractory period is due only to the potassium circuit. And the other question is, are the thresholds for the sodium and the potassium the same? They can be different, but they can also be the same. These are these hyperparameters that one can tune in trying to make the behavior of the circuit match the behavior of real cortical circuits. So if we want to fit data with real cortical circuits, we probably will find values of these V thresholds that are different in order to match the real data from biology. If all we care about is producing some dynamics that resemble action potentials in real cells, and we don't want to really fine-tune the details such that they're exactly identical to pyramidal cells in area 17 of the cat, for example, then we can put them all to the same value. So that's, yeah, these are free parameters that one can choose. And now if we look at the output of the circuit in response to a small step input current, this is what you see here. You see that DMM increases. As soon as it reaches threshold, it spikes. Then the sodium stops pushing, the potassium turns on, it resets, goes back to everything to zero, it increases, and so on. Now here, actually, in this data that is measured from the silicon neuron from one of those chips that was done in the 90s, you see that the action potential, the firing rate, is not uniform. So ideally, if you have a constant current, you would like the output to have a constant firing rate. But here there is this extra channel, the calcium channel, that is not shown in the circuit here, that has an additional effect. The calcium channel is another negative feedback like this one. So whenever the calcium channels turn on, they sink current from the input. And the calcium channels, you will notice from the curve here, are activated not by the input current, but they're activated by the output spikes. So whenever there is an output spike, it increases the calcium channel, which decreases the input current. It subtracts current from the capacitor. So the net input current is the input current that you have here minus the one that you get from the calcium current. So you can imagine if after one spike you have less current, after two spikes you have an even less current, and after three spikes even more. So the more the number of spikes, the less you get the effect of the input. It's like a high pass. So whenever you have the onset, you have a high frequency. You can see it here. But the more the calcium channel current increases, the lower the effect of the input until you reach some steady state. And so it's not really visible for low input currents, but for high input currents, which is this third type plot here, you see that at the onset, you have a high frequency. And as your calcium channels are also slow, as they increase their current, they subtract even more and more. And at some point, you reach a steady state where the final firing rate is the adapted lower firing rate as compared to the input. Again, spike frequency adaptation is a property of real neurons as well. If you measure data from cortical cells, you will observe exactly the same behavior. In fact, this spike trace here, if you show it to a neurophysiologist, they will not be able to tell you whether it's coming from an electronic circuit or a real neural circuit, a real neuron. And maybe the other thing you should notice is this long refractory period here. This is because also the potassium channels are very slow. There was another question, is GK setting the potassium conductance? Let's go back here. GK is setting basically the potassium conductance exactly, and the maximum, if you go to the saturating part, it's basically IK is equal to IGK. So it's setting what is the maximum amount of current that you can subtract. Sorry, I think in terms of dynamics, the V tau K is setting the dynamics. So I don't know what you mean by conductance, but it's setting, so GK is setting the maximum amount of current that can be pulled away from the capacitor. V tau K sets the dynamics, so the time, how long this effect lasts and how long it takes to build up. So it's, it's the combination of the two in terms of conductance, but the temporal part is set by VK and the amplitude part is set by GK. I hope I was clear, but you can see it here. The long-lasting effect here is changed by changing V tau K. Okay. Yeah, so this was basically, as I said, this was really a breakthrough in neuromorphic field, and everyone was excited. They thought they could build silicon cortexes and silicon brains, and then we realized it's actually more complicated, not only in terms of electronics, but also in terms of once you have all these neurons, suppose I could give you 1 million neurons on a chip with these circuits, what do you do with them? And that's more like a theoretical question, not a technology question. The other point that you should be aware of is that this is one neuron. It uses many transistors. Each of these symbols is 5 transistors. now with the progress in technology, the number of transistors doesn't really count. But if you want to have these temporal scales, where here you have 50 milliseconds, you need to have very small currents and very large capacitors. And so what dominates the area in these circuits is always the capacitance. So you might be able to make these transistors really tiny, nanometers or micrometers, but capacitors will take up, hundreds of square micrometers. So it's still not scalable. In order to put 1,000,000 neurons on a chip, you would require a very large area, like centimeters square, or even more, on a single die. The other disadvantage of the circuit is the fact that we're using sub-threshold analog circuits and many transistors. And you know that analog circuits are affected by device mismatch. So even though you can copy paste the layout of these circuits and have identical copies in theory, when you fabricate these chips, there will be differences in the voltage thresholds of the transistors, in the geometry. And so even though you copy paste identical copies of these neurons, if you inject exactly the same input, you will start seeing slightly different outputs because of these device mismatch effects. And the larger the transistor count, the stronger is this device mismatch effect. So in this circuit that has many transistors, there is quite a substantial device mismatch effect. So if you have 10 neurons, for example, and you get one neuron to fire at 100 hertz, other neurons could be firing at 80 hertz, 120, maybe even 50 and 150. So there's a huge variance in the properties of these neurons. And it's something that you might want to avoid if you want to do high precision, spiky neural networks. Or if you want to have a distribution of activation functions, like in some competing paradigms, then it's actually a feature. You get this variability that in software you would have to simulate with some random number generators. Here you get it for free. So it's either you try to minimize the effect of mismatch if you want to rely on high precision, or you find computing paradigms that are compatible with, or actually even require, variability and inhomogeneities. And then you can use these circuits and you get those variabilities for free. So it depends at the system level and at the application level, if this is a good circuit or a bad circuit to use. Now, if assuming we want to have a bit more control on device mismatch and we want to reduce this variability, which is actually quite substantial here, one way to do that is to simplify these circuits to have many less transistors. And as I told you, in the 80s, Carver-Mead proposed this axon-hillock circuit that was very influential. And so I want to show you this axon-hillock circuit that is the opposite side. It's really, whereas this is one of the most complicated circuits that one can design to implement silicon neurons, the axon-hillock is one of the most simple circuits. And so we see the two extremes. And then we will finish the lecture by seeing something in between. So the axon-hillock circuit is this one. It's really simple. It has, of course, you need to inject input current into the neuron to make it fire. It has a membrane capacitance node here. It has a non-inverting amplifier, which brings the output to the two extremes, either ground or VDD. And then it has a positive feedback pathway with a capacitor and a negative feedback pathway with some active elements. So it's still inspired by the way that real neurons work, with sort of sodium positive feedback and potassium negative feedback, but it's much simplified. So the way this works is that you inject current, the input current goes into the VMEM and it increases VMEM. In this case, okay, let's assume we are at a steady state where everything is switched off. The VMEM is 0. This is non-inverting amplifier, so 0 in input, 0 in output. If the output is 0, this NFET is switched off. So this pathway is completely closed. There is no way for the current to go, and this is a capacitor. So at resting conditions, when we start to inject input current, the membrane current, the current can only go into the capacitor. There is nowhere else for this to go. We have infinite impedance here. This is switched off, and we have infinite impedance here. Actually, it goes into this parallel capacitance arrangement. And so Vmem starts to increase linearly because it sees these capacitors. So we have CdV dt. So if we have constant input current, we have a linear increase in Vmem. When Vmem crosses the threshold of the amplifier here, the output will go from the one rail to the other rail, to 0 to VDD. So that will then turn on this transistor completely, which will then activate this pathway, which will allow the capacitor to discharge if the current flowing through this pathway is larger than the current coming in. So if we have a small input current and a large discharge current, after the neuron spikes, after Vmem reaches threshold and Vout goes up, Vmem will start to go down again. And then this capacitor here is important because it implements positive feedback. We'll actually see all of these in detail in the next few slides. And you realize that when Vmem discharges, it actually goes down. At some point, it will go so low that it will cross the threshold of the amplifier again. Vout will go back to 0, and so everything will be reset. So let's look at it in details. How does this actually work? And here are some traces measured from actually, no, these are just hand-drawn to explain what's going on. So again, we inject constant current, we look at Vmem, we start from initial condition in which there was some charge on the capacitor, but everything is switched off. So Vmem increases linearly with the current. As soon as we reach the spiking threshold of the amplifier switches, and the output voltage, which is digital, that would be the red trace, goes from 0 to VDD. Now, I told you there is this positive feedback effect. So here, the effect of that is that actually, because Vout goes from 0 to VDD, this big jump in the output has a big effect on the input. And Vmem sees this jump on the output and just follows it. Then Vout is on. Then we turn on the reset transistor. Vmem starts to discharge. And then if we reach the threshold of the amplifier, Vout goes back to 0. Now, this plot here is showing what could happen if you have the up threshold different from the down threshold. So if your amplifier has mismatch, or the thresholds for turning on are different for the thresholds for turning off, you would have this condition. Otherwise, the green trace would go all the way back to the dotted line. Sorry, I'm checking the question again. Is using the same transistor in parallel and in series a widely used technique in neuromorphic, or is it too costly in area? Oh, this is related to the previous circuit to avoid mismatch. It's different techniques actually for avoiding device mismatch. Typically, we try to do analog transistors large, and then also so that helps in reducing device mismatch. Increasing the area, the W and the L of the transistor, decreases the effect of device mismatch. But also having dummy copies or having multiple copies of the same instance is another trick to reduce mismatch. And so one can combine the two techniques. One can either make single transistors very large, or one can make large transistors, and then to further reduce the device mismatch effect, to make copies of those to either increase the effective W or increase the effective length, depending whether you put them in parallel or in series. And this is actually the same technique also used for capacitors. The way to have good matching in capacitors, which is important, for example, also in the Axon-Hillock circuit, is to make a unit capacitance. And then if you want to have one capacitor, which is, I don't know, 10 times larger than the other capacitor, is to have 10 units in one case and 1 unit in the other. Or if you want to do it twice, you could have 10 units and 5 units, and so on. So these are techniques that we actually teach in the NE2 class for learning how to reduce the effective device mismatch. But going back to the axon Hillock circuit, this is basically showing how the circuit works. And it's important to realize that this is a high gain amplifier. And so V out really goes up quickly as soon as Vmin crosses the threshold. And so this is showing the effect of this high gain amplifier. Now, the first thing to study is how much is this jump that Vmin sees with this positive feedback? Why do we need this capacitor? You could imagine, actually, this is actually another anecdote I'd like to tell you. You might not need this capacitor. What would happen if we did not have this capacitor? So we would have an input current, Vmin would increase, it would make V out switch to high, but then without the positive feedback, Vmin would not see this change and would just stay where it sits. It would just start to decrease here. And then V out would go back and we would repeat. Vmin would just go up. It would not spike. It would just start to reset. It would discharge, it would switch, but V out would still be a nice digital pulse. So you could still create spikes, digital spikes at a rate that is proportional to the input current. So it works as an integrated fire neuron, but without having the positive feedback. And this was actually tested. One of the first axon Hillock attempts was actually done without using this positive feedback. But now you have to imagine what happens if you're in the real world and you have your chip, it comes back, you inject current, you start to observe on the oscilloscope what happens if you have, I don't know, picoamp currents, and you have a physical system, you're actually close to it, you know, you're measuring from it. And you start to measure on the oscilloscope these traces. What would happen was that the circuit would not work at all as expected. And you have to imagine, let's look at this green trace here. And you have to imagine now in a physical system, you always have noise. So the green trace would be superimposed through small fluctuations that are there due to the noise. So if you get close to the spiking threshold of the amplifier and you have noise, when you are close enough, you will have the amplifier switching up and down with the noise. So you would start to produce bursts of spikes that are actually correlated to the noise and not individual spikes with a frequency that is proportional to the input. So you have to have a positive feedback mechanism that actually kicks you away from the threshold, from this high gain region of the amplifier, such that you're above this noise margin. And this is sort of a lesson that was learned from engineering that explained to the biologists why real neurons have to waste so much energy to produce this big jump up, this spike. Why do you need to activate these sodium channels? If you do have noise like you have in the nervous system, you really have to go away from this high gain region to be able to cope with noise margins. And this is an example of how by building silicon neurons, at least those biologists like Misha and others understood better why real biology, real neurons have certain mechanisms. And I hope it's clear to you too that you need positive feedback to have robust computation. Otherwise, any noisy signal would make you switch at the frequency of the noise. Okay, so how does this positive feedback work? It's very simple. It's a capacitive divider. All we need to ask ourselves is, given that we have a change at the output node, how much is the change on the input node? That's what we want to know. If V out goes from 0 to VDD, how much is this green jump here? And that's easy to do. You just need to realize that this is a capacitive divider and that you have some constant charge, you have conservation of charge. So you can just write down the equations and solve it really easily. So, but I'll do it for you. If you have a delta V2 on the output, which is going from 0 to VDD, you have to first to assume charge is constant. So the charge on this plate is the same on the charge on the other plate. And you look at delta V1 and delta V2. So C1 V1 plus C2 V1 minus V2 is constant. And if you have something constant, the deltas will lead to zero change. If you have variations, there is no change. So then you can say that C1 delta V1 plus C2 delta V1 minus delta V2 is equal to zero. And that basically allows us to figure out, given delta V2, what is delta V1? And that's this simple equation here. So this is, it's a classical capacitive divider ratio. And the height of this jump really depends only on these two capacitances and on delta V2. Delta V2, we know it's VDD. So the height of this jump is really VDD times this ratio. And so we have it here. The positive feedback is really nice because it allows us to basically, by changing the size of the feedback capacitor compared to the membrane capacitance, we can set what is this noise margin that will kick us away from the switching region so that we can have robust current to frequency conversion. And yeah, so this is basically the, sorry. Now let's look at how the frequency changes with the input. So this is explaining why the positive feedback is important. But now, just to be a bit more quantitative, I told you it's a nice circuit that converts currents into spike rates. So we want to know, given some input current, what is the output firing rate of the circuit? And to do that, we need to measure essentially these two periods, the TH and the TL period, the period in which V out is high and the period in which the output is low. And those really depend on, on the input current and the reset current. So if you think about it, the period in which the amplifier is low depends on this ratio here, on is inversely proportional on the input current. Depends on the total capacitance that the input current sees, which is the sum of the two capacitors, divided by the input current times this delta Vmem. And the delta Vmem is, we know from the capacitor divider ratio from here. So if we replace this delta Vmem, we can get this period. And it makes sense. The smaller the input current, the longer it will take for the capacitor to charge. So the more distant the spikes will be, the larger will be TL. So TL is inversely proportional to the input current. And TH, on the other hand, is given by this discharge rate here. So it depends on how much current is going out of the capacitor versus the current that's going in. So it depends on the IR minus I in. And again, on the total capacitance and the delta Vmem. So again, we replace delta Vmem from the previous equation, and we calculated, and you see that now the period of V out being high depends on, essentially on the difference between the input current and the reset current, which is non-ideal because ideally we would like to have a circuit that produces pulses that are a constant width. And so this is actually not ideal. It's possible to fix it by adding extra switches, but one easy way to fix it is to say, I'll just make I reset orders of magnitude larger than I in. So if I have picoamps in input current and microamps in the reset current, then this term, my IR minus I in, the minus I in becomes negligible. And then you basically have a pulse width that is independent of the input, essentially independent of the input current. And that's what typically is done with these axon-Hillock circuits. You can really have relatively constant pulse widths. And what really is important is that you can control the pulse frequency, so 1 over TL. And that really depends only on the input current. Okay, so this was actually, oh, sorry, my camera switched off. My camera froze. I'll just switch it off. I don't know if I can from here. This was the axon-Hillock circuit, but we still don't know if we want to put it on chip. We still don't know how to implement in CMOS this amplifier. So what is the easiest way to implement a non-inverting amplifier? And the most compact way, it's actually to use two inverting amplifiers. So if you have a NOT or an inverting amplifier, and you just have two of them, then you can implement a non-inverting amplifier. And I hope you remember how this works. Basically, if your input is low, the output is high. And if your input is high, the output is low. It's just an inverter. And this is actually what was done in the early 90s to implement the Axon Hillock circuit. And again, a historical note is that when the Caltech team developed the chip that implemented this circuit, in the end, when they got the chip back, it was burning a lot of power. I'm trying to get the camera to work again, but I think the battery is dead. So why is it that this sub-threshold circuit here that's using picoamps was burning a lot of power? What was the reason for having picoamps in input and just resetting things burning a lot of power? I can't look you in the face. I can't ask you questions. I just have to give you the answer straight away. But the reason is relatively simple. If you think of it, you have input currents that are very small. We want to have biologically realistic, dynamics. And so these voltages here are increasing over tens of milliseconds. And so when you reach the spiking threshold, the inverter's inverting threshold, you will be hovering around this threshold for some fractions of milliseconds. So that means that when you're hovering around the inverter's threshold for fractions of milliseconds, you have both PFET and NFET fully on, and you have a short circuit between ground and VDD for fractions of milliseconds. So this is shown here. This is just a transfer function of the inverting amplifier. So if your input is low, your output is high. If your output is high, if your input is high, your output is low. But when you're in between, you're switching. And if you look at the current flowing through the amplifier, the inverting amplifier, the current is maximum when you're exactly in between. And that's why this circuit is burning a lot of power, because we're using analog current dynamics to drive digital circuits, which will then be in this open state for milliseconds. And this is really something that is not feasible, especially if you want to have like 1 million neurons on a chip, and all these neurons are switching with these millisecond dynamics, then your chip is going to be burning tens or hundreds of milliwatts. So what is a solution to solve this? It's not clear. There's many attempts. One way to do a low power non-inverting amplifier is just to use the transconductance amplifier, like we saw in the lecture of the transamp. In that case, you have a two-terminal device on the input and an output here. If your bias is in subthreshold, this would be a low-power amplifier, and you can explicitly compare the membrane potential to a threshold. This was actually done in a analog circuit design of a silicon neuron in the, I guess, late 90s, when they were still trying to figure out how to solve this power consumption problem. And it's shown here. This is one of the circuits. It's very similar. You basically replace the two inverting amplifiers with one transamp and then the two inverting amplifiers. So the transamp is nice because it allows the output to go from 0 to ground very, very quickly, even though the input is hovering around the switching threshold for milliseconds. So you have here a high gain stage, which takes slow changes in the input and makes fast changes in the output. If you have fast changes here, then having an inverter is not a problem. And then the second inverter never was a problem because the output of the first inverter also is making very fast changes. So the only problem was with the input to the first inverter, but if we have an amplification stage at the beginning that makes the changes fast, then we solve that problem. So in this circuit, you also see uh, other series transistors in the inverter, which are making the inverter what is called a starved inverter. You're limiting the current that can flow through with a subthreshold current. So this is yet another way to reduce power consumption. And finally, there is, in this last inverter, there is this extra starving transistor, which limits the current, but there is also an extra capacitor here. So here you should notice, let's see what happens. If we increase injection current, Vmm increases. As soon as it crosses the threshold, the input goes up, the second inverter goes down, the output goes up. Now, if the output is up, it charges this capacitor here as well and turns on the reset. Now we turn on the reset, Vmm goes down, this goes up. When this goes up, it turns on the NFET and it allows current to flow through the VRFR transistor. So the charge in the CR is discharged through this VRFR. And because this is now starved, it's a very small current, this V out is not going to go down quickly. It's actually going to go down linearly at a rate set by this reset current, the VRFR current. And this slow down trend of V out essentially implements a refractory period, because V out now does not go to zero right away. It stays high for some period, which depends on the size of the capacitor here, CR, and on the size or the amount of current, the RFR. So now we have something that at least can implement a refractory period, which can then be used to set the saturation of the firing rate in a sigmoid-like fashion. And let me show you some data from this old chip. This was actually using synapses as inputs. So whenever you had an input synapse, it would produce some current that would go into IMEM. The IMEM would charge Vmm up, and then eventually you would reach V threshold, which in this case was set to 2.5 volts. It would spike, it would go down, and the V refractory period was, the V refractory voltage was setting the refractory period. And in this case, it was, this is in, it was maybe tens of milliseconds. By changing the refractory period voltage, you could make this period longer or shorter, which would then make the neuron saturate sooner or later. And this is showing the FI curve, the firing rate in response to the input current. And so here you see a first example of real data measure from one of these silicon neurons. But again, now you can imagine this starts to be somewhere in between the Mahowald-Douglas neuron, the conductance-based version, and the axon-Hillock neuron. And it doesn't have the advantages of either. It's not small enough that you don't have mismatch, and it's still simple that it doesn't reproduce the biophysics of real cells. And so it's not really the ideal solution. And that's why the community, students and researchers kept on investigating other ways of doing neuron designs. And this is actually still an active area of research. There are still many, many groups in the world that are trying to make new neuron designs to try to solve different problems. But let's look at what we came up with as the neuromorphic community, as the groups around the universities in Caltech, in the Maryland, in Europe, in Zurich included. So the idea is really to have something that's in between the very, very simple models and the very, very complicated models. And this is a diagram that represents the Hodgkin-Huxley equations or the Mahowald-Douglas neuron. So, we, as engineers, we would like to find a circuit that can bridge between the two. But fortunately, also from theoreticians, sorry, there was a question on VBP on the previous circuit. it's connected to the first and to the second. So this bias voltage here is a subthreshold bias that's making this current very small, and it's making this current also very small. Sorry, here. That's making this current very small, and this current also very small. Sorry, I was saying we would like to bridge the gap between simple and complex models with somewhere in between, and as engineers, but also theoreticians have the same problem because they either have to implement very complicated differential equations that implement Hodgkin-Huxley, or trivial differential equations that then can be used for making very large network simulations. And the neuroscience community actually came up with a suggestion that then is ideal also for the circuit design community. And let me show you that. This recently is actually now quite old. It's been more than 10 years. In 2004, there was the group of Wolfram Gerstner from EPFL from Switzerland actually proposed a generalized integrated fire model that could actually approximate real neurons with a very high detail of accuracy, degree of accuracy. And then these were actually shown to be ideal also for predicting real neurons. So these generalized integrated fire neurons became more and more popular and are actually very nice models that allow us to implement optimal circuits. So here, this is the basic description of a generalized integrated fire model. If you look at it, the integrated fire equation is this first one here. You have a membrane potential that increases linearly with an input current. And then the idea is that if it crosses a threshold, you reset. And if it doesn't cross a threshold, you just increase linearly. The generalized term includes an extra function that depends on the membrane potential. And this extra function, depending on what you find, can be more or less difficult to implement in silicon and to simulate on a computer. For example, Idzikevich found that if you have a quadratic term of UMEM, you can implement it very efficiently in MATLAB or with numerical simulations. And Gerstner found that if you have an exponential term, which of course includes the quadratic terms, then you can actually approximate biology really well. So if you're doing DSPs or FPGAs, or just if you want to have very fast numerical integration methods, and you want to be close to biology, the best thing to do is to use a quadratic term here. And this is the model that was proposed by Idzikevich some years ago. If you want to model biology and fit data from biology really well, you have to use an exponential. So exponentials, require floating point units. They're not ideal for FPGAs, but in subthreshold analog circuits, you already know that implementing exponentials is really easy. So for us, this is really nice because we can implement the exponential integrated fire neuron really easily. This is numerical simulations from computers where you have the exponential, and the blue is the data from real pyramidal neurons of cat visual cortex, and the red is the solution of these differential equations where f is an exponential with a positive exponent. And even if you zoom in really well, you can see that it approximates quite well, at least at the first, for the first instance, the data from real cortical cells. And so this is an example of a neuron that implements exactly those equations. If you see here, these equations, I'm going a bit fast because time is running out. But these equations essentially are showing how you have first order differential term, conductance term, constant current, and then an exponential term. And it's a two variable system. It's a coupled variable. The fast variable is the membrane potential. And then there is a slow variable, which here it's called W. It's kind of misleading because it's not a weight. It's just the name of a variable, which is a slow variable that is also a first order differential equation. And it has a negative effect on the fast variable. So this is equivalent to what I was telling you at the beginning as the calcium concentration. The larger this W variable, the less the effect of the input current. It's I minus W. And so if we look at the circuits that implement these equations, this is the circuit here. And if you, it's a current mode circuit like we saw before. So you have input currents, you measure output, you measure a current here. So that would be the output current. And you also have a DPI synapse, differential pair integrator synapse here, where have input currents and output currents. So if we look at this IMEM, and if we look at this IG, and we write down the equations for them, we can then find a set of equations which is equivalent, formally equivalent to this set of equations here. And just trust me that if you, this IG, you should remember from the DPI lecture that is really first order. If we assume that the input current is larger than the leak current, then the BLK-AHP in this case, we can write it as a first order differential equation. And the neuron also has a differential pair integrator. So if we assume that the input current is larger than the leak current, we can also simplify this equation to a first order differential equation. So that would be the simplification. But now, not only there is this DPI, there is also this red circuit that has this positive feedback. It's a positive current. And this IA current is actually exponential with the membrane potential. So this F of IMM is an exponential term. And we can write down the equations, but it would take some time. But you can imagine that you have a positive feedback. The stronger the input, the larger the feedback current, the larger the feedback current, the bigger the membrane potential, which increases the feedback current even more. So you have this avalanche effect that you also have with the Hodgkin-Huxley equations. That's with a positive exponent. And this is data measured from this circuit, from a chip that has this circuit, fitted with these equations, where F here is an exponential with a positive exponent. So you can see it fits really, really, and you know how difficult it is to fit exponentials. So you can see that it fits this really, really well. Now, if you keep on injecting current into the neuron, you will keep on getting spikes in output. And now you have a two variable system where they interact. It's a physical system. So this is actually a chip that has, thermal fluctuations. You have picoamps, so they're comparable to the currents due to thermal fluctuations. And you can see that if you have picoamps in input, you have very low frequencies. This is, half a second. And because of this influence from the thermal fluctuations, you have variations in the output. You have variability. And again, you can see this as a feature or a bug. If you want to have stochastic computing, you need to have a circuit that can naturally produce random outputs. And so in that case, this would be a feature. If you want to do high precise computation, then you have to you rely on less noise. So you would have to inject much larger currents. You would get much larger frequencies, but then it would be less influenced by thermal fluctuations. So this is just to show you that if you do want to have Poisson or close to Poisson spike trains, which you might need for some computing paradigms from some theoretical reasons, this circuit can actually give you that without having to have explicit random number generators or some complicated random number generator circuits inside. It's already built in. And then, of course, if you change the parameters of these circuits, you can change the behavior of the circuit as well. And both Idzikevich and Gerstner show that with some parameters, you can actually model what is called bursting cells, cells that have this type of behavior here, that when you inject input currents, they start to fire with a very high firing rate. Because of this low variable, which is equivalent to the calcium current, they adapt. This is zooming in the first few spikes. And they adapt so much that they subtract such a big amount of current from the input that the neuron stops firing completely. When everything goes back to zero, the slow variable recovers slowly, goes back to zero as well. So then you're not subtracting anything from the input. The input starts to have an effect again. You start firing again. Then you adapt, you subtract, and so on. And because of the thermal fluctuations, you also don't have deterministic output. You have a stochastic output also in the bursts. So this, again, is a feature of a bug. If you want to model bursting cells, like in the thalamocortical loop of the visual cortex, this is a perfect model of these bursting cells. So it's a feature. But again, if you want to have a closed control loop with very tightly balanced control variables, this is a bug. You should not be using this circuit. Then, of course, you can put many of this. So now we have a circuit which is relatively complicated. So it does have device mismatch, but it's not as complicated as the Hodgkin-Huxley circuit or the Mahowald-Douglas circuit we saw at the beginning. It only has two differential pairs, and then it has some inverter sequences. So the inverter sequences, you can use minimum size transistors. They are not affected by mismatch. And these two differential pairs, you can try to use large transistors to reduce device mismatch. So it's a very good compromise between the very simple and very complex circuits. We have somewhere in between. But in addition to being able to model real cortical cells and fit with the state of the art from theory, the really great advantage of this circuit is that it's ultra low power. It's been designed to minimize power consumption. And the reason that this is ultra low power is that there is this positive feedback. So as soon as you start to turn on the inverter, which then will burn power, you take the same current that's flowing through the inverter, which is the cause of the burning power, and you send it back into the input, which makes the input increase even more, which switches off the inverter really quickly. So that's the reason why this is so low power. As soon as you start to burn power, you switch off the circuit that's burning the power. So this is this positive feedback. This actually came out of a competition from students in the Telluride workshops that proposed this solution to reduce power consumption. And only after we realized that it actually matches the equations from Gerstner and his group. So it was first designed because of engineering principles. And then only after we found out that it actually matches cortical circuits really well. And now you can put many of these on chip, and you can then see how they behave like. So here in this data is an example of 32 neurons on an old chip, where we start from, I guess we start from here, where we inject small current. Of course, they all have different initial conditions. So the neurons, depending if the capacitor is discharged completely or has some charge on it, it will reach threshold sooner or later, and then it will start to fire. And then if your current is constant, the firing rate should be constant. And you can see that there is some noise, some variability, but more or less all of these neurons fire at the same firing rate, average firing rate. And if you increase the input current, you increase the frequency of these spikes. And you can see it even here. So this is with small input currents, higher, higher, and then higher again. And the layout of these circuits is relatively small. Here is an example of a layout where you see the membrane capacitor of the circuit is this big red square. And below this other rectangle is another capacitor that would be the refractory period capacitor that implements the refractory period. And then everything else is, whenever you see the red and the green cross, that's a transistor. And the blue is metal lines that are connecting all the nodes together. So this is a simplified version of the circuit of the schematic that I showed you, but essentially it's an example of a layout of a neuron. And then you can imagine you can copy paste these, and you can put hundreds or thousands of them on chip, and then you can have your large neural network chip. Again, remember that doesn't solve everything, because these chips only do what you tell them to do. If you inject current, they can only spike. And so now the complicated thing is, how do you connect synapses and neurons and then arrange them in a way that they can actually do some functionality? And that's more a problem of theory and modeling. And then once you know what neural network you want to do, then you can actually take these building blocks and put them together on chip and build your ultra low power spiking neural network processor with these chips. And these circuits that I showed you, these are sort of state of the art. As I told you, it's a hot area of investigation. This was already done 10 years ago, but variants of these have been proposed even in the latest ISCAS 2020. So it's still very hot topic. And you have on your class chip this circuit and other variants of the circuit that you can measure from. And you will also measure from the axon Hillock circuit that is also on the chip. There's only one of those, so even though it burns power, it's not going to compromise the chip. So it's no problem if you keep it firing also with very small currents. Okay, so let's go on to the last slides. Actually, I just wanted to hurry up so we would have some extra time for questions. But now I told you we can put synapses on chip, we can put neurons on chip, we can connect them together, and then we can use them to do basic research, like trying to understand why some configurations in biology are arranged like that, and then from engineering principles try to understand why and explain and justify them. One nice example was the positive feedback that was found necessary in the axon Hillock circuit that explained why you need positive feedback in biology. And it's the same reason why we need positive feedback in this circuit here. Not only is it useful for reducing power consumption, but it also kicks you away from the noise region where you would be affected by noise. So also here, this positive feedback is explaining, it might be that it explains why you need it in biology, because it can reduce power consumption also in biology. It's actually the most effective way of reducing power consumption if you have these activation channels and inactivation channels in engineering. So it might very well explain also why real neurons have these activation currents, the sodium activation currents in biology. So basic research is always one sort of common thread in some of the activities that is being done around the world, and in particular at the Institute of Neuroinformatics when we try to build these chips. Of course, you can use these circuits to encode signals. As you've seen, these are actually very nice A to D converters because they take analog currents and they convert them into frequency of spikes, of digital pulses. And so if you have like a microphone or a pressure sensor or a temperature sensor, and you would like to transmit the value of these signals using low power circuits, rather than using standard power hungry, but very precise, I should say, A to D circuits, if you're not interested so much, if you can tolerate noise and you can build classifiers that can tolerate some amount of noise, then these spiking neurons are very nice A to D circuits to put directly on the sensor and convert analog signals into pulse frequency modulated signals. Finally, of course, the ultimate goal would be to have the whole loop, to have sensors, spike processing, and then motor actuators to have a complete robotic agent that is using the same building blocks that biology uses, like a bee. That, again, could be used for low power, low latency products to solve real world applications, or it could be used for basic research with this idea of understanding by building. And then there is this trend or hype, I should say now, in AI, artificial intelligence, where people use neural networks for all sorts of computations. For example, for detecting all the pictures of cats that you have on your cell phone. The current state of the art is being done with GPUs and dedicated digital logic with sequential digital logic neural network accelerators. But there is this need also there to have very low power, and digital logic by nature is not optimizing or minimizing power consumption, whereas these circuits, the synapses and the neurons, first of all, they're completely passive. You should have noticed that there is no op-amp that is always on. Only if there is a spike does the DPI allow current to flow through its transistors. And so only if there is data, there is power being burned in the synapses. And the same for the neuron. The neuron circuit that I showed you only has passive components. So there is no constant bias that's turning an op-amp on here at all. Only if there's input current, you charge up a capacitor, and only if this capacitor exceeds a threshold, you turn on an inverter and you activate some reaction chain. So if there is no data, there is no power being burned. So these are ultra low power, and they might be appealing technology for low power computation in those cases in which you don't need a floating point high precision. So if you need high precision, still it's very difficult to convince industry to use these technologies. But for example, if you're doing edge computing, Internet of Things, if you want to convert biosignals, for example, from t-shirts or headbands when you go jogging with very low power circuits, this technology is very promising. And now there are even startups that are starting to come up that propose to use this technology for creating these types of products. In fact, one I should say is from the Institute of Neuroinformatics, is called SynSense. And basically, I would say that more than 50% of the people working there are ex-INI students or INI postdocs that are trying to really, make it big by selling or making products using this technology. Yeah, as I said, I wanted to leave some time for questions. I'm sorry that the camera, the batteries just ran out, and seeing how the output frequency changes depending on these parameters. Maybe there is even the chance to look at the Axon-Hillock circuit. And then if you want to getting the spike frequency adaptation to work, this behavior here, where the slow variable turns on, that's an extra credit exercise where you will have to change also even more parameters. Instead of switching this green block completely off, you can turn it on and then get this behavior. Otherwise, you would observe behavior of this type where you just have uniform firing rate in response to uniform current. Yeah, so with this, I'd like to thank you for your attention. But again, I